Now, whenever we deal with aqueous solutions, we can't really talk about things as far as grams go, because everything is dissolved in solution. And once something's dissolved in solution, because there's water there and there's your stuff inside the water, we can't talk about it in terms of volume, right? Because your stuff is dissolved in water, but it doesn't tell you how much stuff is inside the water. So we have to deal with terms of concentration, okay? So in chemistry, when we talk about concentrations of solutions, we generally deal with this big term. Big M. And big M stands for molarity. What molarity is equal to is the number of moles of solute dissolved in every liter of solvent. All right? So if you have grams of solute, you can figure out the number of moles of solute as well. Okay? So to give you an idea how that works, if I have grams of material, if I divide the grams by the molecular weight, grams per mole, which is molecular weight, of the solute, this ends up giving me moles of solute. So another way of looking at this, if I'm giving grams, right, is I can substitute this relationship in for moles of solute. So big M is going to be equal to grams of solute over molecular weight of solute times liters of solvent. All right, a little bit of a manipulation there to get down to what I'm dealing with. Okay? But essentially, if you can find moles, you're in good shape. And molarity is always related as moles over liters. So both those terms are interchangeable. Okay? And this represents concentration. Now the good news about this is that in a laboratory environment this is perfect because everything's climate controlled. Temperature doesn't really vary that much, so all the volumes are going to be the same. Now, when I get to places where the temperature isn't the same, say I'm going out with Doctors Without Borders and I go out to Kenya, and I'm in Kenya, in the middle of Kenya, and it's 115 degrees, and I've got my little serum bottle that's been bouncing around in the back of a Land Rover for the past 100 miles. Well, the volume inside of that, it's going to increase, right? Because as things get warmer, they're going to expand. So you have to be careful that you use molarity in a laboratory environment only. If you're using it outside of a laboratory environment, there's a different concentration value that we're going to teach you later on that we're going to use. But for right now, we're just going to stick with molarity. Okay? So let's do an example. Suppose I have sodium hydroxide. Excuse me. Sodium hydroxide, NaOH, and the molecular weight of this thing is 40. Okay, I did the calculation for you in my head. So if I have, let's see, 120 grams of NaOH and 4 liters of water, what is my molarity? Okay, now go ahead and pause. Try to solve this problem first on your own, use the information that you've got, and then hit unpause and then watch how we solve this. All right? Now in this case, I'm looking for molarity. All right? So I know that big M is going to be equal to the moles of solute. Well, I was given grams, not moles, but I do have the molecular weight of sodium hydroxide. So I'm going to substitute grams per mole, or grams over grams per mole for my moles of solute here. So I've got 120 0.00 grams of NaOH, starting information. Okay. Now I'm going to put in my molecular weight, which has to be on the bottom. 40.00 grams of NaOH for every 1 mole NaOH. Right? At this point, this is molecular weight. Okay? And this is going to give me moles. Right? The last part that I'm going to use is the liters of solvent. And I'm going to use 4 liters of solvent here. And at the end of this point, I'm going to have a unit which is moles over liters. So at this point, I'll be able to find my molarity. Okay? Now I do the math here, and what I get is this value. I get 120 over 160. Okay? And what do I get there? What's my value? Good. 0.7500 molar is what we're going to call the concentration of that solution. Okay? So that means for every liter of the solution, I'm going to have 0.75 moles of sodium hydroxide. Pretty concentrated solution. Okay? So this is a basic example of how to do things. We'll do more examples in class like this. So I'm going to move on. We're going to talk about what to do when you've got to dilute or concentrate a system. All right, for a dilution, what we're going to do is we start off with a concentrated system, and then we're going to go ahead and dilute that concentrated system. So, for example here, I'm going to start off with the equation, and then I'll go ahead and give you an example to work with. The dilution equation is going to be C1 V1 is equal to C2 V2. In some books you might use, it might be M1 V1 times M2 V2. I like using C because C is a concentration term. And concentration is universal. So if you're using a different concentration value, right, if let's suppose you're using molality or you're using percent weight per weight, that also works in this dilution equation. If we just use M, we're just talking about molarity. So I wanted to be a little bit more broad, which is why I'm using C1. So C is concentration, okay, of my first system. And over here with V, I'm going to have my volume of my first system. My second and my concentration over here, my second volume. Okay, so this is it's a very simple equation to use, and it's easy to rearrange in order to get where I need to go. So let me give you an example. Suppose I start with a 5 molar NaOH solution. And the question is, how much would I need to dilute to a 100 milliliter 1 molar solution? All right. Now the important part in these problems is to look at the question and pull the relevant information out of the system. Okay? So I start with 5 molar. So let's go ahead and I'm going to mark up my problem. I'm going to write in here, I'm going to say 5M is going to be C1. So I'll call that C1. All right? And the next number I get to a 100 mil. So I'm going from this solution to a second solution. So first solution, second solution. So I'm going to use my second volume, V2 over here, that's my volume, right? And I'm going to use molarity here to be my second concentration. So I'm going to rewrite this in terms that I know, okay? So I know C1, I do not know V1, and I know that this is equal to C2 and V2. I know both of those. So I'm going to rearrange to get something that is isolated on one side of the equation. So I'll divide both of these by C1. So now to solve this, all I have to do is take V1, and this is going to be equal to C2V2 over C1. Now, since I've already defined my variables in this problem, all I have to do is put them in the equation and do some calculator math. Okay? So V is going to be equal to 1 molar times V2, which is 100 milliliters. All of that over 5 molar. Now notice that the concentration value is going to disappear at this point. And this is why it's nice to use C1V1 equals C2V2, because the concentration terms disappear, or they're always going to be the same as the previous one you used on the other side of the equation. Okay? So my molarity cancels out, so I've got 1 times 100 over 5. Okay, so what's 100 divided by 5? That's right, 85,000. No! 100 divided by 5 is 20. So my answer here is going to be 20 milliliters. Now, how do I do this practically in a lab? I'm glad you asked. Glad you were thinking that. What I do is I start with my beaker, and this is my 5 molar NaOH, and what I'm going to put this into is something called a volumetric flask. The volumetric flask kind of looks like this, okay? And it's got a point on here, and this point is the 100 milliliter section on the volumetric flask. What I do is I pour in about 20 milliliters of my 5 molar solution, and then I'm going to dilute this with 80 milliliters of water in order to get to my 100 mil point. When I get to that 100 mil point, I now have a solution which has been diluted down to 1 molar. Okay? And that's how we use these dilution equations. All right, the last thing we want to talk about with this is that we want to examine, since we talked about concentration, it's natural at this point to go into acid-base chemistry and pH. Well, pH is a measurement of how much H plus is in a system. And remember, if you think about HCl, when this hits water, it dissociates into H plus and Cl minus. What we're going to do is we're going to measure the amount of H plus that's in a system. Okay? Now the first thing that you should note is that water autoionizes. What does that mean? I'm glad you asked. If I have 2 water molecules, they dissociate to become H3O plus and OH minus. In all water, if it's just regular pure water, this H3O plus, the concentration of this, and that's what these brackets mean. These brackets mean concentration. The concentration of H3O plus is going to be 1 times 10 to the minus 7 molar. And guess what? The concentration of OH minus is going to be the same thing. All right? So everything starts at this value. If I add HCl to something, I'm going to bias the amount of H3O plus here and raise the concentration of H plus and drop the concentration of OH minus. Okay? So to measure these things, I have to use a pH equation. In my pH equation, anytime I have P is going to be equal to the negative log of whatever I'm looking at. Negative log of X. For pH is going to be the negative log of H plus concentration. So if I have something that has a pH of 4, it's going to be acidic. So let's look at the pH scale. Here's pH. Here's my concentration of H plus. And I'm going to put concentration of OH minus over here as well. Okay? And I'm just going to pick out a couple of important points. And the first point I'm going to use, of course, is 7. And at this point, pH 7 means I have 1 to the minus 7 molar. Okay, both these concentrations are in molarity. And 1 e to the minus 7. Okay, for both of those. If I look at pH 4 and pH 1, Now this jumps to 1e to the minus 4, and this going goes 1e to the minus 10. If I go to 1, that's 1e to the minus 1, 1e to the minus 13. Okay, and if you think about those numbers, 1e to the minus 1 is 0.1 molar, so it's actually quite concentrated. This one is 0.0001 molar, and this one is 0. There you go, that molar. Okay. Now, if I go the opposite side of the scale, if I go to 10 and 13, let's do 10 and 12, this now drops to 1e to the minus 10, which means that this is to the minus 4. At this point, I've got more hydroxide than I do H+. All right? Notice that both of these values, my H+, my OH values, both of them are going to equal 14 at any given time, right? 12 and 2. So it's 10 to the minus 14 for both of those concentrations when they're multiplied together. All right? Okay.